Maybe this meeting is being recorded. Thanks. Welcome everyone to the third day of this NSM mini course on concurrent programming. So far we have looked at concurrent objects and linearizability. And yesterday we looked at memory consistency models and coherency protocols. Today we are going to look at some interesting aspects of related to synchronization, which is going to be covered by Dr. Saurabh and Dr. Praveen. Dr. Praveen we know who took the first lecture and is also hosting this meeting. So let me introduce specifically Dr. Saurabh today.
No. Actually, today whole lecture will be covered by Dr. Saurabh itself.
Oh, I see. Sorry about that. Yeah, thanks, Dr. Praveen, for clarifying that. So, Dr. Saurabh Kaikar is a research scientist in the parallel computing lab at Intel Labs, Bangalore. He completed PhD from IIT Madras, and his research interests lie in parallel and distributed computing, compilers, and architecture-aware optimizations. His PhD thesis focuses on locking protocols for parallel accesses to the in-memory hierarchical data structures. He is a recipient of the Institute Research Award at IIT Madras, Distinguished Paper Award at PPOP 2016, and winner of Intel's Parallel Coding Challenge at HIPC 2016. He's going to talk to us about synchronization primitives. Over to you, Dr. Sir.
Hello. Hi. Thanks, Rupesh, for nice introduction. And I would also like to thank NSM for giving the opportunity for everyone to learn high performance computing as part of this NSM program. And we have already gone through a couple of lectures on this concurrent programming. And now we are going to see the third lecture on the series. I hope you all are enjoying so far that how Praveen and Kalyan have nicely covered the important topics of basics of concurrent programming. Like Dr. Praveen and the initial day, first day, he covered that how we can leverage better speed up with the help of multi-core architecture. And then Dr. Praveen also discussed how we should ensure the consistency and correctness of program. And then in terms of hardware and cache memories, Dr. Kalyan covered how whole hardware comes into picture when it comes to the coherency of different multi-core systems and their cache coherency. So today in this journey of exploring concurrent systems, we are going one step forward and we are going to see how we can think in terms of concurrent programs. Like concurrent programming is not an engineering, it's an art. So sometimes it doesn't come naturally to us whether the program is parallelizable or not, and if at all it is, how should we do that? And while designing the concurrent algorithm, we also need to ensure that there are certain scenarios where we need to avoid. There are a lot of challenges while dealing with shared memory, and also how thread communicates with each other. And there are also a few aspects like given that all constraints of shared memory and how we should ensure that correctness of program, we also need to ensure that we are achieving the maximum concurrency. So given that we have multi-core systems and multi-threaded program, it doesn't mean that all threads will essentially go in parallel. They may get blocked, they may mess up shared data, and there are a lot of challenges can happen. So all these aspects of this concurrent programming we are going to see in this today's lecture. As I said, concurrent programming is an art. So we need to think in different programming paradigm, because we as a human being have trained ourselves over the years how we think in a sequential way. Because if we think a task can be viewed as a set of different instructions or different sequence of micro steps. For example, if you ask any small school going kid, how do you plant a seed? He can also come up with a proper set of instructions that you first have a seed, then dig a small hole in the soil, put the seed, cover the soil, then water it, and so on. So it also comes very naturally to us. How do we think in parallel setup, right? And in this case, if we want to think in a parallel way, we also need to see that how can we distribute few small chunks of these steps into different workers. So like if you have a job of doing some marketing, so you can ask 3 of your friends that, okay, you go buy this thing, I go buy this thing, and you have suppose a number of such friends, you can do your shopping in a lesser amount of time. So always this embarrassingly parallel behavior of algorithm doesn't appear in the real programs. So there can be scenarios where you need to coordinate between each other, and we need to think in that aspects. When I say that we have trained ourselves in terms of sequential algorithms or sequential programming, that also was one of the reason that the traditional computers were single threaded. Or like if you see in few decades back, you did not even have multi-core systems. And we have already covered a lot of things that we hit the power wall, then we could not increase the frequency, and then we had to fall back to multi-core systems. And then there was a challenge for software to utilize that hardware. And the hunger of this better speed up was not always just because someone wanted to just play a video game with a faster speed and they don't want any delay in their experience. There was always high level. There was always a high level. Okay, Rupesh. Okay, my screen is not shared. Okay. Okay, I'll wait for a while and let me see if I can share my screen. Is it visible now?
Yeah. Can you go to the full screen mode or presentation mode?
Yeah. Is it fine now?
Yes.
So
Can you minimize a bit?
I'm presenting my PPT slide here.
Yeah, we can see the screen.
Okay, that's great. Okay, so here we were. So I was talking about how we came to the multi-core systems, and then there was a better motivations for having those multi-core systems and the performance. As we are saying that everyone, the buzzword you have heard about ML, AI these days, and you might not have imagined the advancement which the last decade has in this space without the help of multi-core systems, multi-node clusters, and so on. And nowadays, this machine learning and AI are crossing the boundaries so that the things which never were imagined, like the advancement in digital biology, digital chemistry, physical simulations, and whatnot. So it's like a virtuous loop between now computing and the physical modern science as well as fundamental research. So a brief about my Intel lab. As I said, this HPC also motivating machine learning, AI, and AI machine learning is also motivating other aspects of science. So we at our Intel lab, we also do research towards what would be the next generations of hardware. So eventually we need to solve the real problems, and the architecture research should also align to the requirements of the applications. Like biological domain might have different requirements than a physical simulations. So such research will be a future directed research, and that's how we will move from the multi-core systems to whatever next generation systems will appear. So this is a big umbrella of all HPC, AI, parallel computing. So now we will again come back to our today's topic. We are going to continue our journey, how we can leverage the multi-core systems. And so far we have seen in the course basic constructs of concurrent programming, how multi-threaded systems can help you achieve better speed up, and what are the cache coherence protocols, and what are the details of every small operation in the cache. Like complete hardware is supporting you, how you share the data, share the memory, and you must be appreciating the details and the beauty of those complex protocols, how every shared and exclusive blocks communicate with each other, and so on. So today we are going to cover the topics of thread synchronization, and we will also see the construct which are used in parallel programs for achieving those synchronizations. So I'll start with a very basic example of a mathematical operation, vector addition. So you all must be aware of a small array, suppose array A, array B, and you want to do a vector addition of A and B into C. So eventually you want to add location wise the sum into C. So let me take a laser pointer. So you are adding 1 plus 2 equal to 3, 3 plus 4 equal to 7, and so on, right? So suppose you have a single threaded program like a for loop here. That loop is going from 0 to 1000, and every iteration you are adding A plus B equal to C. And hypothetically assume that every addition takes 1 millisecond. In practice, it doesn't take that much. It will be very few nanoseconds. But for simplicity of our calculation, let's take 1 millisecond, and you have say 1000 such additions. So this sequential for loop will take 1000 milliseconds at a time, right? Can we do it in parallel? Yes, because every addition is independent of each other. So if we have multiple threads, you can actually process these things in parallel. So how simple is this? Just one liner. Suppose you are using a OpenMP framework, OpenMP library in your CCPP style of program. Just adding hash pragma OMP parallel for will do your job. It will internally split this iteration into multiple chunks based on your threads in your system, and it will also collect the data into C. Simple, right? Any chat here? It's or 5 haven't we? Okay, it's old. Okay, fine. So let's take another example here. Sum of array elements. Suppose you have again array A, and now you want to do a horizontal sum of all the elements and accumulate into a suppose value. So this for loop from 0 to 1000 goes over every element in A. It should be A actually, not C. So sum of A of I, and then it collects the value into sum. Correct. So now if we do again same thing, hash pragma OMP parallel for, will this parallelize this loop, and will you get the correct sum? Right? Anyone has any comment on this? Because I guess if we have interaction, then I guess it will be a very useful talk. Yeah, as Mayank is saying no, Krishna is saying no, correct. So because this sum is a shared variable across all different iterations, the final value of sum will get a different value, which might not be as exactly same as it should have been. But if you say in OpenMP, do you have any support for such things? Yes. So if you just add reduction and plus operation, so essentially if you think in an intuitive way, what it does, it partitions the iterations and then collect a partial sum for each of those partitions, and then eventually accumulate it into the final sum. So this program will correct fine with the operation of reduction. So reduction means whenever the mathematical operation is commutative, so like A plus B plus C can also be written as A plus B first and then C, or A separately, B plus C. So such operations can be framed as a reduction, and you can use OpenMP pragmas. Now, before going details of all such shared memory and all these things, I would like to first introduce the basic difference between process and a thread. So process everyone knows, right? So when we compile a program, you get a binary or any application in your computer. So open PowerPoint, Word, everything is in process. So a compiled sequential program can be viewed as a code portion. It also has a global data. It also has a heap memory, and it has its own set of registers and its stack. So what do I mean by code and global data? So if you try to understand from this sample code, so whatever is the written code here, that can go as a code section of this process address space. There is a chat. Is there any feature for directly pragma for parallelizing code block? That must be there in all languages. I think these days do support internal parallelism. Anyway, we can take such questions later. I'll read those chats once I have a proper time to pause. Anyway, so you have a global data which can go into the global section of this process address space, and heap memory, whenever you allocate anything from calloc or malloc, that goes into the heap section of your address space. and registers are CPU registers, and stack, every function has its own stack. So eventually a process itself has its own stack. Now, unlike a process, so process can be viewed as a logical entity which runs on CPU. And suppose you have this program and you compile it, you get a process or you get a binary which you run on your CPU, and also you open another terminal and open same binary and run it. And so now if I have this global data as 0, and suppose somewhere I update this variable inside this main. So do you think that two process will change this data in a shared mode? Anyone has yes or no view? Okay, so yeah, so because I said that they have different address space and they have different global data as well as heap, so it won't interfere. And if they want to at all interfere, they can interfere through a shared file system, or there are sophisticated way using MPI, message passing interface, that two processes can interfere. Now coming back to threads, multiple threads come into single process address space. Like, so they all share code, they all share global data, they all share heap memory. So here heap allocation is shared by multiple threads, global data shared by multiple threads, and but their registers and stack are separate. So what do I mean by these things? What is separate and what is shared? So this global data, if multiple threads share, means if one thread is updating, other thread can actually get the updated value. But unlike global data, if you consider stack, so for this function add, right? So if this add function is getting called by multiple threads at this call, so this is pseudo code for multi-threading parallel, and you add a plus b equal to c sum. So this sum value is separate for each of these threads. They don't interfere with each other because this stack for this add will be separate and the address space itself will be separate for these two threads, right? Fair enough? Or any doubts on this? If no, I can go one step further. Okay, so let's start with a simple example. We all know that these days we do online shopping on Flipkart, Amazon, and everyone must have faced one problem. So at one point you check whether there's an atom in your cart, like the stock is available, and tomorrow you open and the stock is gone, right? And even if you check another, then you may get stock again back. So these are the two sample functions which I have tried to simulate this operation, where add to inventory function is intended to add new quantity to a certain atom, and before doing that it checks whether the stock is less than my maximum capacity of my, say, warehouse. And then if that is the true, then I do stock value equal to stock value plus my new quantity, correct? And another is a function which does a process order operation. Suppose there is a process which tries to buy a few items, so order size is there, and in the function we check that whether the current stock is greater than my order size, then I'm fine to buy, and then internally the server will decrement the stock by the order size, and eventually you run the sell operation. Now take example, suppose you have an add operation of 5 quantity and there is a process for 4 items. And now there are 2 different threads which are running these functions in parallel, right? So suppose thread 1 is doing this, thread 2 is doing this, and both things are running in parallel without any intervention, because any user can place order at any point of time, and any, say, inventory controller can add this. So what would be the final value for this in this case? So I would like to take input from audience here before going further. Okay, so anyway, so we can continue to dissect this further. Okay, what is that? Could anything depend on the order? Exactly correct. What is max capacity? Max capacity is any value. Suppose you have a warehouse which only can accumulate 1000 items. So suppose you have a room where only 1000 boxes can be placed. So this is just like a logical entity where it restricts to add infinitesimally stocks. And yeah, it could be dependent on the order. right? Suppose there is a timeline T0 to T3, and as suggested by Mayank, that suppose at T0, someone that the inventory addition checks the max capacity condition, and at T2 there's a parallel thread which is checking the order size with the stock value, and at T2, because the operation is satisfying the condition, it is adding the inventory, and finally after this the order is also decrementing it. So after this, what all the possible values for this? So as he said that let's not worry about what is the outcome of this and move one step further. Suppose this is the timeline and final value might be 11, because suppose 10 plus 5 15 minus 4, or 10 plus 4 10 minus 4 6 plus 5 11. So if you follow this timeline, you might get answer 11 if you consider this as a interleaving of the instructions. But hold for a minute, we'll see another example. Suppose there are two threads who are both are doing process order. Example is very simple. Maybe you must have gotten the glimpse of it in the first lecture itself by Praveen. So stock equal to 10 initial value, and then two orders for 6 and 8, and same timeline, and how timeline is appearing. So at time T0, this condition checked stock is 10. At T2 again stock is 10 for second thread. At this thread, because T0 is correct, saying true value, then it is decrementing to 4, and this is decrementing to 2, and then boom, things went wrong. So what would be the value of stock at the end of this parallel execution? That depends on really what was the interleaving. So it may be 2, it may be 4, or a very undesirable thing -4, right? And all these things depend on what are the real interleavings of these instructions. Is called as race condition, because the stock value is shared across multiple threads, and if you do not take proper precaution while doing these updates, so you might get any value based on this. So if you want to enlist all the issues in this program, so the very first thing is the if condition is true at time T0 for thread 2, but it got violated at timeline T3. So at T0, what happened? This guy checked the condition is true. So for this thread, there is no mistake in the logic. This guy is checking it, and if it is greater, I am fine to buy. Then he decrements it. But because someone at T2 already changed the value from 10 to 4, that is not visible at condition, because this condition is already executed. And because of this update, we will not go back in time and again recheck the condition, because we don't even know what happened in between. At this time, T1 and T2, anything and on a number of instructions can get executed by a number of threads, and we don't have any idea what happened. So time to check versus time to update is different. And another thing is the load from the memory or load from the local cache. So when T2 updated this value, as you studied yesterday, so because of this update, the cache will do invalidations for other local caches of thread T2, but the update might be in the channel, so it might not have reached the cache of the local memory of thread 2, and it might be just in between. And so there are three chances: either it is invalid, so thread T2 will fetch from the main memory, or the update has not reached, so it can be read from the local cache, and a number of such ways are possible. The operations are non-atomic. So as I said, this if condition and stock updation, this operation collectively is not happening as a one operation, because at this time it is checked and it has updated. So logically it should be happening either both or none. And this, as I said, a check and decrement must happen in an atomic way, right? Any doubts till this point? Anyone? Any confusion about sharing or interleaving of threads or interleaving of this timeline? Okay, good to go. So what do I mean by non-atomic operation? So one thing was when we say this if condition and check is non-atomic, that is correct. Collectively, this must be appear as the atomic operation. There is another small loophole in this. When you say stock equal to stock minus 10, so in this example, I have just marked it as at time T3, this thing happened, but it doesn't happen like that. because this instruction is made up of small different steps. So if you want to convert this instruction into an assembly instruction, it will be first you are loading the value of stock into the register R1. And register means all ALU operations only get performed on the CPU registers. So everything which you want to operate on must be there in the register. And then you are performing a subtract operation. That is, you are subtracting say 10 from the value of R1. So now at this instruction, there is no connection between your stock, means whatever is in the memory, and the R1 is independent, just carrying the value of the stock at that time. Okay. And now third operation is the storing of this R into the stock. So eventually you are writing it back into stock. So load, operate, and store are the three steps which are getting performed as part of this small single step. Fine? Any doubts? Okay. So now we are now at the point where we can discuss data races. So data races means the condition where a shared data is getting updated, and the basic condition for that data race is you need 2 or more threads. So even if you have a multi-threaded program and there is only one thread running, so you won't face any data races. And there should be a shared memory access. So it may possible that in the first example of vector addition, you did not have any shared access, right? In this case, although you have multiple threads, but there was no sharing of memory, so there will not be any data race. And even if these two things are there, at least one thread should be performing a write operation, right? So if one thread is writing it and other threads are reading it, then only there can be a data race. If all are readers, then there won't be any data race. So some comment is there, no doubts. Okay, cool. So now we will discuss thread synchronization. Thread synchronization means suppose you have a set of parallel threads and they have a job to be performed. And if the operation is not embarrassingly parallel, you might need some communication between threads. And the way these things should be communicated should be a very precise set of rules, and every thread should be agreed on the set of rules to be performed. And this is called as synchronization protocols. And to perform such protocols or to implement such protocols and design a parallel algorithm which is thread safe and it should not have any data races, there are constructs provided by the generally these threading libraries like Pthreads or any language which provides those parallel threads. Typically, they are categorized into logs, barriers, conditional weights, and atomics. So now onwards, we will discuss each of them in slightly details and how they perform, what are the properties of that, and how and when should you use either of these construct at proper places. Okay, so the basic construct of log is mutex. Mutex stands for mutually exclusive logs. It ensures that when you use them properly, so your shared data is protected, and it also ensures that only one thread at a time can execute in the critical section. So critical section means the place of your code or a portion of your code where shared memory is getting updated and accessed, right? So eventually it protects the shared data from undesirable outcomes. Now again, let's go back to our example where we discussed the adding of inventory and process order. And we have also seen that because these are non-atomic operations, we may end up into undesirable outcomes which we do not want. So we'll see how we can fix this problem using mutex logs. So suppose you have a mutex type of T and the mutex variable is stock log. So view this log as a shared entity across threads, and it only exchange their hands when one thread finishes and transfer it to other. Not actually transfers, the one who is waiting for it, it will get it. Suppose there are 10 people and there is just a ball which one holds for some time and then releases it, and then other one guy comes and holds it. So that holding is a operation on locks, and the ball itself, in example, is a lock variable. So in this case, the stock lock is the lock variable, and there are two operations getting performed on this lock. That is acquire lock, which grants you the exclusive access to the lock, and there another is a release lock, or you can say unlock. So for example, in this case, at the starting of this operation, you acquire this lock, and then you perform this operation of if condition and increment it. Now make sure that once the lock is acquired, n number of thread, although they are processing either add inventory or process order, they won't get this lock because it's already acquired. And at the end of this, once you finish your operation, you unlock the lock. Fair enough? Very simple construct, mutex, right? Similarly, for process order, you also design the same protocol. You acquire the lock before you want to access the shared variable stock, and finally you unlock it, right? So placing of this lock and unlock at proper places comes under the premises of designing a lock protocol. So in this case, the lock protocol simple would be, before using any shared data, you just lock the lock associated to that shared data and then unlock it. I precisely used the variable stock underscore lock because this lock is only guarding the shared data at location of stock variable. So there could be another shared variable, suppose maybe at any user database which some operation want to operate on. So this lock might not guard that if you acquire this lock. So that would be a different lock for that operation. So generally locks are associated with the piece of data you want to guard. Now, if you perform this operation of whatever order you want to perform for T1 and T2 for inventory 5 and 4, it is guaranteed that you will get the value 11. So there are only two possible chances. Either add inventory will happen first or the process order will happen first. So there is no confusion of any other interleaving of the steps, right? Now, I'm slightly changing the process operation into something else called as inquiry. So we know that when we check any order or any item for stock, that happens more frequently than we buy. We just love to just go and visit the Facebook, Flipkart site and see the stock available or not. So these operations are more frequent than actually you buy it, correct? So if as I said, I designed the protocol. If you want to share the data, you place the lock before and after the access. And there are two such things. And in this case, if at certain time instance, there is no one actually adding the inventory, but there are many more inquiries happening, right? So in this case also, acquire lock and release lock are placed around this shared access. And the question is it safe, right? Yes, it is safe. And the problem would be performance, because there is some comment, it is slow. Yes. So because we are only allowing one thread to go in parallel, only one thread can inquire, and other threads will just have to wait indefinitely. Wait time is more, correct? So eventually we don't want to restrict such readers from going in parallel. So what could be the another solution? So this problem is fixed by reader-writer locks. The idea is multiple readers which do not modify a shared state can read the shared data, and multiple readers can also read the data in parallel. And if there is at least one writer currently writing to the data, no other reader should be allowed to execute that critical section, correct? This means the protocol, if you have to summarize it, multiple readers can read in parallel, no two writers can write in parallel, no two reader and writer can execute in parallel. So this means reader is an exclusive access candidate, and writer is an exclusive access candidate and reader is a shared access candidate. we'll see how we use these reader writer logs in this scenario, right? So now there is a different type of log, reader writer log, which has a stock read write log. And now we redesign our protocol so that add inventory function will acquire a write log on the shared data, right? So the acquire write log, so write is the word which we use to distinguish between read and write mode, and there is a log variable, and at the end of it you unlock it, correct? And now the same inquiry function, what it does, it acquires a read log, then there is a flag which says uh, the stock is not available. Then if you find the stock is enough for your order, you say the flag is true and return the flag, right? And then we unlock it, correct? So now in this way, you get a better degree of concurrency by allowing multiple readers to run in parallel. There is a small issue in this. Suppose there are 10 readers reading the data. So there are 10 inquiries happening in parallel. And now at a time T1, there is a writer who wants to write to the stock. That is add inventory function is getting called. So now because the protocol says that all readers are reading, so no writer can write. So writer will have to wait till all the 10 readers finish. So it waited, then he was in a waiting queue, say that 10, 9, 8, 7, 6, 5. And at 5, there were 5 more readers appeared. Then again counter became 10. So there could be an infinite waiting time for a writer. So that means there could be a starvation for the writer. So how these problems are solved? So typically, if you consider a case of Pthreads, so there will be a mechanism which typically ensures the fairness. So there might be a waiting queue which says that first come, first serve, and then after the writer is there, the next 5 readers will stand in the queue after that write. So that way you will get a fairness of that writer will not wait for indefinitely, right? And these things are the way these things are coordinated are dependent on the different libraries. So the fairness protocol, there is no standard way. So there can be different scenarios like, okay, the write operation is not that prioritized, but readers are more at higher priority. So in such cases, the reader might get higher priority than read, and so on. So there might not be any proper answer to such fairness questions, right? So now when we consider this mutex log, reader logs, when it comes to implementing such things in a software, so simple answer is they are not as easy as it looks like. Before implementing a log, so what I mean by implementing, I'm not saying that you use the log and guard your function. I'm asking the mechanism that is getting provided by this acquire call and release call. The mechanism itself must be implemented somewhere, right? So implementing such function calls, that's what I'm referring to as a log implementations. So to implement such logs, you need a proper understanding of the hardware, what it supports, what it doesn't support, what is the memory consistency model, strong, weak, and so on. There you might need to use memory fences, volatile data types. The memory fences means the instruction which forces you to flush the data into RAM. So flush as in, suppose there is a variable which is getting written in a L1 cache and you place a fence operation. So fence operation forces the process to whatever is there in the cache, you write it back to RAM. So such mechanisms you might need to use while implementing the log. And then log construct should also support the properties like fairness, liveness, progress. So these terms are very involved. Fairness means every thread should get equal opportunity to acquire the log. Liveness means if some thread goes like a down or it dies, so it should not restrict other threads to perform other operations. And eventually the concurrent program should do a progress in whatever condition, it should not stuck in between. So there are different challenges while involving such things. So there is very classic algorithm for giving the demo example of such log implementations called as Peterson log. So it supports two process solution when you have thread 1 and thread 2, and then how the log can be implemented. So I'm not planning to cover these things today in this topic. And if you are interested, so there is already a course under NSM by Dr. Rupesh Nasre. You can follow this link, and there is a very nice explanation for this log implementation for Peterson log. So let me pause for a while. I think there are some comments. Via strong weak memory models. Okay, so this is slightly off the topic for this, but yeah, I can answer this right away. So strong and weak memory models are to ensure your correctness of. So yesterday you consider, right, when you have a cache coherence protocols and how caches are interacting with each other. So ideally what should happen, that suppose some thread writes to a memory and another thread is reading it. So in ideal scenario, that write must appear to that reader no matter what it should be. But if you really want to implement such strong consistency, so the performance of the CPU will go for toss. So it is like a compromising between the performance versus your correctness. So generally, the modern CPUs do not go for strong consistency. So they go for a weak one. So weak one means there is a fair guarantee that how it is implemented. So it guarantees, suppose that whatever write you have written on a memory, it will eventually reach to RAM. So the word eventually means there won't be any scenario that your write is lost in between the channel, but it doesn't guarantee that it is getting written at that certain point of time. And that's why we are advised to use these log constructs and all those things to consider there is a weak consistency model and still how you should ensure that your program is correct. So it is between like a compromise between performance versus the hardware support for your concurrent program. I hope this answers your question. Right? Should I move forward? Thanks. Okay, cool. Okay, so given that we have discussed read-write logs, mutex logs, let's discuss some interesting scenarios of these logs. So now again, let's revisit our inquiry function where you have a operation of add to inventory and an inquiry. So I have a question for you. Why do I need reader log? Can't I just read it? Right? So if I just want to inquire stock, whether it reports me 10 stocks are available or 15 stocks are available, I don't bother. And the operation is not that critical for me. So should I just remove these logs? So I would like audience poll for this argument. You can unmute yourself or chat. What do you think? So yes, Krishna is saying we can remove these logs. Any other opponent party which says that it must not be removed? Yeah, there is no fun if there are no two parties arguing with each other.
So what if I'm reading the whatever variable I'm locking in, and so while I'm reading, someone goes and overwrites the value? Like that could happen. That could probably lead to some problems.
Yeah, that is true. Suppose at a point t0 there is a value say 20, and when it actually reached to you, it was 10. But in this case, the inquiry might be wrong. So it may be 10 or 20. But in this scenario, that might not affect my purpose. So yeah, so there is no right or wrong answer to this question. So updated value missing. It is not missing. It is just read at a wrong time. And if you re-inquire it, it will be different. So basically these things are possible. You can do such things, but you have to also ensure that what are the data types you are reading or writing to. So I would not confuse you audience. So what should be done? So that depends on what are you going to perform in this operation. Suppose the difference between primitive types versus user defined types. So primitive type means integer, float, double, and all those standard types which are supported by hardware, as well as compilers do generate proper instruction for it. So hardware ensures that the writes are atomic. So there won't be any case that suppose there is a 64-bit integer that 32 bits are getting written from first write and 32 bits of MSB are getting written by other write. So that won't happen. So in this case, it will ensure that whatever the value you read, that would have been valid at certain point in time. So you either get true for this or you get false for this. So this condition will say true or false, right? But if you have a user defined type, suppose you have an object which says the data for a person, name, age, gender, and then you perform such operations and you try to read such things. And it might be the case that you read name as Alex, which is male, and the gender itself is a female. So there could be some mess up between these two fields of that class because that doesn't fit into primitive type. So in this, let me check the comment. Can also happen with long string. Depends. I think long also fits into the primitive type. It is 64 bits, so 8 bytes is supported in most of the hardwares. Strings are not primitive types, so string can be broken into different pieces. String is not, long should be supported because it is a primitive type. And the other aspect, so even if you have primitive type, so that doesn't suggest that you can go log free. Although primitive types are there, then the important thing is what you are going to do with the data which you read, right? In this case, you are just deciding, okay, the stock is there or not, but there might be other critical decisions based on this condition, whatever the value you read. Okay. Can also happen long read. I didn't mean long as a data type. Long means large string. Yes. Long string, yeah, strings are not primitive types. So string, you know, right? When you allocate string, it just points to the starting point and it is just a sequence of bytes. So string is not primitive. So that is possible. That is surely possible. Good that we are on same page. Yeah. So I have an example for this. Suppose there is a case one, the thread one going to write a value 10 and 20 at different time instance on the same shared data, and thread 2 is reading the same value at two different time instances. So what can be possible? So once this write happened, this read happened within a time, and this write reflects in this read. And then second write performed, it was also in a proper time premises, it also got on the read as a 20. So 10 write, 10 read, 20 write, 20 read. There might be another interleaving which is possible where thread 1 write 10, but the value is not getting read by thread 2 within that time frame, and the thread again overrides this value to 20. There may be some n number of operations happen between this, but we are only considering the operations of our interest. And in this case, because these operations are getting reflected after this second write, both the read operations will read the same value. Fair enough? Any confusion? Okay, good. So this scenario is very interesting. This example reflects the timestamp of the operations which read is getting performed. Just 1 second. Good. So I would like to share one very interesting story with you. Have you ever heard of the Pthread 25 keyword? Any one of you? Anyone of you is aware of what it is and what it is about? Okay. So there was a very interesting story in the past. So Pthread 25 was, okay, later I have some comment. Okay, no. Okay, so let me share one story with you. So in late 90s, so there was a computer-based radiation machine which was getting used for cancer treatment. So the machine used to set a laser beam, and there would be a localized pointer which burns the tumor of cancer patient at certain affected area, right? So earlier versions of this machine used to be mechanical. There used to be mechanical functioning and manual intervention of users. And then this boom of software and the speed of software came. Then as other tools, this also moved from hardware-based thing to a computerized based. And what it used to do, so there was a table which sets the position of the patient. and there was a laser beam which needs to be set at proper magnitude of the intensity of the beam, right? So in this case, what happened? So once this operations, the tool was getting used, after some time there was some complaints about the infection getting spread into different organs. There was some organ failure, and also there are some deaths for the patient who were undergone through such treatments using this machine. And there was a set of complaints about these things, and do typically happen in hospitals or any legal setup, that the patient condition is generally subjective, so you cannot guarantee that something really works for someone. And this issue got postponed for some time, and when the such cases increased, the deaths increased, the patient who were complaining increased, so there was an investigation for this machine, and it went through a thorough testing. Is there any really a problem with this machine itself? Because whenever the whenever it comes to the correctness of the machine, and the demo was always correct, whatever the machine used to show, the outcome was also the desired outcome. So there was no proper debugging which can show that the machine is a failure. And then after 3 years of investigation, led by a lot of computer scientists, a lot of biologists, a lot of medical practitioners, then there was a long report which reported that there were a lot of issues with the design of the machine, the design specifically of the software of the machine. So I'm quoting here one of the sentence in that report. The design of the software was itself unsafe. The Pthread 25 supported a multitasking environment, and the software allowed concurrent access to shared data. This precarious implementation caused program failure under certain conditions. And this is quoted from the reference of this. So you can go details of this. So what exactly happened in this machine? I think we need to mute one of.
Please unmute yourself.
Am I audible?
Yes, yes.
Okay, thanks, Praveen. So the main bug in the system which was getting highlighted in our context. So there was a shared memory location which was getting accessed for two different operations. So the first operation was the manual who used to monitor the machine used to enter the intensity of the laser beam into one of the, say, text box of the GUI, and that value will get written into one of the memory location in the hardware. And after it enters, the value should be read by the specific the hardware in the radiation beam controller, and it will read the intensity and it will set the intensity to that value. And then the controller will add the value for a height of the table, and the same controller for which controls that height will read the value from the same location. So looks like this interleaving is correct and it should behave correctly. But in very rare scenarios, what used to happen, if the values are entered in a very less time interval, it was the case that first write, which was there for the laser beam intensity, was getting overridden by the value of table, height of the table, and maliciously the read operation used to read the value which is meant for table as a radiation beam. So horrible, right? So the intensity was so high that it was 5 to 10 times larger than the intensity of laser beam, and it affected a lot of patients. And when this report came, then people started understanding what was the real cause. And now here I would like to make you understand that the bugs in concurrent systems are not too obvious, because in general computer science, any sequential program, you have a set of input, set of output, you match the test cases, all test cases are passing, and you ensure the correctness. And because you might be coding for all HackerRank and all such things, you said all test cases passed, boom, I am done. But the bugs in concurrent system do not appear automatically, because the malicious interleaving can really occur in one of the million times. So we do not want that once in a million time situation in such a real critical scenarios. So we will have to be very careful while writing such concurrent programs. So I have one comment here to address. What is that? Quick question: why was the performance important for Pthread? They could have chosen single-threaded application. Difference would have been at max few seconds. Yes, that is there. So I don't know the details of the Thread 25 as hardware or software, but there might be some. It's not about multi-threading. There was like a multiple hardware threads were going in parallel. So we need to study what was the exact Thread 25 software. But there might be some scenarios. There was. I don't have the proper answer for this because I don't know. I just know the incident. But there might be some real reasons for going from hardware to software because of the performance. Because to handle hardware, you need 10 people. Software can do that task without any manual intervention. And also, maybe I'm just giving you intuitive answer. Uh, we always prefer going software controlled things because suppose you ask a person to set a proper coordinate of x comma y, he may commit a mistake, but a computer would not. So software do help in such cases. So maybe that might be some such reasons which went wrong for TOS. But concurrent program do make mistakes at time. Yes, that's what they should not. That's what we should have proper precaution. It may be slow, but you should put proper locks for this. So that's why we have this locking construct and synchronization. Okay, so let's move ahead. So now we will discuss few interesting topics. So if we need a small break, we can take a pause for a couple of minutes and then discuss few more interesting topics. Right, Praveen? It's fine, right? We can take
Yeah,
a
that is fine.
5-minute break for this. And if you have questions, we can discuss in this time. Or any confusion or anything which you want to discuss, you can unmute yourself and we can discuss right away. Okay, let's continue our discussion. Now again, we revisit our program of inquiry. So this is in the context of again read write logs. So now we are going to see few interesting scenarios, right? So the flag again, same example, is stock order greater than this and then true and false. Suppose I slightly tweak this program to something else. And the tweak was already there in the previous slides, but I would like to revisit. So what is the difference between these two implementations? Spend some time to go through each line. So I have removed this flag from here. And now I have converted this implementation. If the condition is true, then I return from true. And then if it is false, return false, then unlock. So what are the differences between this and what are the implications of this? Anyone would like to give their thoughts on this?
So if the stock is greater than the order size in the second case, we might not unlock any time, right? That would like lead to a deadlock because no one else would be able to gather the lock anytime.
Exactly, exactly. So I don't know anyone have observed that bug. So this was the code when I introduced the inquiry, but no one pointed because such bugs are very easy to get missed from a human eyes. Just for a proof, if you go back in our inquiry function very first, right? I ask everyone, is it safe? Is it safe? Everyone said yes, it is safe. So such bugs are very easy to getting ignored, and we need to pay attention. So now in this case, if we are performing this operation, we lock it in the read mode and we check the condition and we just return the function without touching this line, because this line becomes unreachable code for this function, right? And now if the other function which is waiting for a write log, it will waiting for this thread to unlock it, and it will indefinitely keep on waiting. So whole process will get halted and no progress. So this leads to a deadlock. And we have to be very careful in the conditional unlocks, because there might be a situations where you have a piece of code in this if condition and then you selectively unlock it. If you have else condition, then also you selectively unlock it. And finally, there might be a path, control path, which also reaches to the end of the function. So in such scenario, we should be very careful while placing your lock and unlock functions call. So these deadlocks are very undesirable for any concurrent program. Another example would be, suppose you have a operation of account transfer where account A is there, account B is there, and you want to transfer 500 rupees from A to B. So in this case, two accounts are two different entities. So you have two different lock variables, account A, account B, and then you acquire both locks, first A, then B, and then you perform the operation. You subtract 500 rupees from account A, and then you deposit 500 rupees into account B. They are very classic examples of concurrency. You must have heard if you have gone through the database classes, and then you unlock one after another, A and B. Now you have same function provided by UPI transfer functionality. But the one who wrote this UPI functionality also wanted to make sure that A and B are accessed in a proper critical section. So it also acquired lock on A, lock on B, and then unlock. So what will happen here? So in many cases, the both operations will be safely executed and you will get proper execution schedule. But in few cases, there might be a case where first function call is going in parallel with second function call. You acquire lock on A. At the same time, UPI also acquired lock, but first on B, right? Both got the lock which they wanted to acquire. And now this thread goes to acquire lock B, which is currently getting acquired by A. So this thread has to wait for this, and other thread has to wait for the lock A. So this is a deadlock situation. This is waiting for this is waiting for this. So this is a deadlock situation which must be avoided. So what is the solution for this? Any suggestions for solution?
Just flip the order of locks in one of the functions.
Okay, I can flip it. So what if I have 10 such locks?
I mean, then like make a consistent wrapper which will like, so let's say make a wrapper which says acquired lock or something, and then each of these account transfer would be a sub function of that. So everyone has to use this like the outer like locking wrapper, and then they can write whatever they want inside that function. So that would basically force everyone to use the same format.
That is possible. Debit and credit should be separate. What does that mean, Mayank? Mayank, you can unmute yourself.
Yeah, hi, can you hear me?
Hi, Mayank. Yeah.
Yeah, so I was thinking rather make debit and credit atomic statements.
Debit and credit atomic statements. So yeah, actually, eventually this is an implementation of such atomics. So atomics, you mean hardware supported or the software supported?
Software supported, sir. But
so that's what we are trying to achieve here. So when we acquire both logs, we don't want any other thread to update either A or either B. So this is actually a simulation of an atomic account transfer. So account transfer means a debit or credit. So is that what you're saying or something else?
yeah, I was just saying that I just had a confusion. What if we separate the debit and credit statements and use different functions. And
Okay. So you mean when you want to transfer any amount, you say first debit is there, and then you
yes,
credit it. But you will debit
yes,
where? You will debit where?
that is the thing.
Right. So suppose you want to debit. Suppose bank is there in between. So the bank will have to suppose debit the account and put it in their own account, right? That own account also becomes a shared resource. So
Correct.
debit itself is one movement from A to B. So eventually the point I want to make here is consistent structure of acquiring log. Yes. Sagnik Nayak is saying that consistent structure is required. That is true. So basically what can fix the problem is maintain a total order of logs while acquiring the logs. This means if you have suppose A, B, C, D up to n number of such accounts, there should be a proper order that you always acquire log on A first and then B. If there could be something A, B, C accounts, in this case also A will get acquired. There is no need of B, then C will acquire, and so on. So in this way, always at this point, if this thread doesn't get A, it will wait for A, but this thread is still okay to go for B. So I'm talking this deadlock situation in the software premises, right? So if it goes into a operating system level multi-threading, where kernel threads are also getting executed in parallel. So operating system has another mechanism to do this. So it also checks the total order, and also there are some mechanisms called as deadlock detection and deadlock recovery. So eventually if few threads fall into deadlock and they are stuck, so there are mechanisms which detects the deadlock, and then there are recovery mechanisms which roll back some operations. But these things are not in our today's discussion context. So I would leave this till the deadlock and the total order of the logs you want to acquire. So this is one of the solution. Other solution also on the way Mayank, or I forgot who suggested, that have a wrapper on top of all logs, and they can regulate the log acquisitions for each such operations. Okay. So there are other constructs called as barriers. So the way I'm discussing these things like log, mutex, reader writer logs, they are having their own properties, their own benefits, own pitfalls. So it's not like you can use one construct for all such scenarios. So there are scenarios where you need different mechanisms, so like barriers. So let's revisit our first example where we were doing vector addition, and then we were doing a sum of all those things. So now suppose I am using a OpenMP Pragma parallel, which creates multiple threads, and the threads which are getting created in this first outer block, they are running these iterations in parallel. And suppose this barrier is not there. So barrier means I'll tell what it is. So what will happen if you run these things and first thread finishes its addition operation and it is now free, it can just go and start adding it, right? But we don't know which value is getting added into sum. So OpenMP, what it does, it places an implicit barrier. So means once a thread finishes this for loop, it waits till this line till all other threads are finishing their respective chunk of data and then are ready to process the next set of chunks. So this enforces that there is a security line at which everyone will appear, and once they are there, you can move forward, right? This mechanism is called as barrier. So these barrier mechanisms are provided by Pthreads and any other parallel programming libraries that we can place at proper places. There is another construct called as atomic instructions. Any confusion in barriers? Okay. So in atomic instruction, what happens? So hardware itself supports you the basic operations to be performed in an atomic way. So what does that mean? So the way we saw the example, you are checking some inventory and then performing some operations. So we can summarize like a check and then act. So there is a hardware support for such instructions called as compare and swap. So remember that these are non-atomic operations, right? You first compare and then modify. So this instruction, what it supports, it gives you a handle such that Suppose there is a variable a which is currently holding value 10, right? And now you want to write a new value 20 to this a if the previous value is 10. So if you summarize the program like if a equal to 10, then a equal to 20. But in this case, you will have to place the logs before condition if, and then after you write 20. But if you use this instruction, what it ensures that if you perform this operation, this if call will return true if the first operand, which is 10, equates the current value of a. And if some thread is actually changing this value from 10 to 15, so this function call will return false, and you would say the update was failed. And this is how it will ensure without any logs, the check and act operation has performed in the atomic way. Any confusion in this atomics or any doubts? Why, how, when it performs? Okay, so I guess it is straightforward to understand, but not straightforward when we implement it. So there are a few complications of, again, coming back to model, strong, weak consistency, CPP, Pthreads all support these instructions, but they do have some challenges. Like even if you have such instruction provided by, suppose, CPP, it doesn't necessarily sorry, it doesn't necessarily actually happening in atomic way. If CPU doesn't support such hardware instructions, it falls back to log. And why one should go for atomic instruction instead of using logs? Because the instructions are lightweight, and log acquire and log release are costly operations. Costly in the sense that there are many scenarios where you have to update a shared state, like you need to maintain a waiting queue, right? So if mutex is there or reader writer log is there, you need to maintain a queue for different readers, writers. So there are things involved, and in this case you are not maintaining anything. So if this operation fails and you still want to write it, you have to keep writing till you get your desired condition checked, right? Okay. So now at this point we have covered the basic constructs like logs, mutex logs, reader writer logs, barriers, and atomics. And we also saw the scenarios where deadlock can happen, then where you can miss out the mistakes in your concurrency, like early return from the functions. And now I would like to discuss a scenario which also explains you all these constructs in a Pthread setup, and have some exercise how we can devise a parallel algorithm for a specific use cases. So this is another stopping point. If you want to have any discussion or confusions, we can discuss. Okay. Now we are going to go through a interesting exercise. We will design a game, right? So the game is something like you all have seen Olympics, where we have a relay race. So there are suppose 2 or 4 players which are running a same race, and then when one player reaches to certain point, then it exchange that ballot, and then other player will start running, it will exchange the ballot, and so on. The one who wins wins the race, right? So there's a mechanism of exchanging ballots. So I would like you to understand this scenario as a concurrent program. Right? Suppose you have 4 teams, 4 different colors, and each team has 2 players, P1 and P2. And when the race starts, the P1 should run till this point halfway through, and then P2 should start running once you reach till this point. Clear enough? And once all these players start with the respective timeline, once who wins or reaches this point wins the race and holds the win flag in the hand, right? The problem is clear. So it happens like this. So I spent enough time to make this animation working, and hopefully, thankfully, it is working fine. So this P2 won in this case. Maybe he is a Hussein Bolt. And now we want to implement this setup in a parallel programming fashion. So the rules of the game are something like this. You have 4 teams, 2 players in each team, and race starts only when all the teams are ready. So player 2, P2, starts running only when P1 reaches the halfway mark, right? And the player of the team who reaches first finishes the race. And it is guaranteed that only one player is the winner. So there wouldn't be any sharing of the winner. So there would be only one winner who holds the flag first, right? So now any design suggestions, how should we implement this? I would like to have user like audience interaction in this and see if we can come up with a solution which implements this thing. We'll first logically solve the problem and then we will go how we solve with the Pthread setup. And then that way also we will discuss how Pthread works. Anyone would like to unmute yourself and have some suggestions? Please come forward, and that's like a exercise which you want to solve collectively.
So what is exactly what are we coding for exactly in this? Like,
So we want to code something like this. So each player is a different thread,
okay,
right? So
Okay.
everyone is a player. Everyone is a different thread which can run independently. And now we want to coordinate the communication between those threads,
okay.
right?
So basically, for example, the blue team, I want to coordinate the communication between P1 and P2. Is that what this is?
Exactly.
Okay.
So P1 should coordinate P2 that this guy has reached halfway mark and the P2 should start running. That is the one feature of this game. Second feature is the one who wins the race holds the flag. So there would be only one winner when you reach the full way mark here. And another condition is all teams should be saying they are ready at the starting of this. So there should not be any scenario where say P1 thread is not ready and other team started the race. So that would be unfair. Yeah. So how should
So
we? What all construct should we use here?
So maybe one like weird idea could be, so let's say there is a referee which is standing at the starting line, like that could
Correct.
be some other thread, right?
Mhm.
Now, what can happen that before the race even begins, every one of these teams says that I am ready, I am ready, I am ready. And the referee will only say that, okay, you can go ahead after like it has got confirmation from all the teams, right? Now,
Okay.
what happens is from the team's perspective, it will say I am ready, and then it will wait for the referee to say, yeah, go ahead, right? So I say I'm ready, and then I will wait until the referee says that okay, now you can go ahead. So that would like set up the starting condition, right?
Correct.
Right. The other thing,
Excellent.
the similar thing would be for like when the switch is happening between P1 and P2. P2 will
Mhm.
continuously wait, saying that unless and until I get a confirmation from P1 that it has reached the halfway mark, I will not start. And similarly, when P1 reaches the halfway mark, it just sends out a communication saying that okay, I have reached the halfway mark, and now you can go ahead. Right.
Correct.
So P2 will wait until P1 reaches and then only it will start. And then finally for the win flag, again, there could be a single lock or something, whichever thread reaches there first takes the lock and that's it. Other threads will always be kept waiting and only the first one to get the lock would, let's say, like basically get the flag.
Correct. So what all construct we can use here? What all things we have covered so far? So how will we ensure that the referee is saying yes and all teams are communicating that they are ready?
So maybe a barrier could be there. So
Okay, good.
in a sense that the barrier is that everyone has to come from being not ready to ready, and that the barrier is just after ready. So until every team is ready, none of them can pass.
Of every team means every thread, all players.
Yeah, every thread. Yeah,
Yes,
in a sense.
correct.
Yeah. So after every P1 is ready, only then any one of them can pass. So
Correct.
that could be a barrier, right?
Yes.
And for P1 to P2 transfer, that could be like a single lock. P2 keeps on waiting for a lock, saying that acquire lock. It's just an infinite loop, and
Okay.
basically once the loop exits, then it can start running.
Correct.
And like P1 initially starts with having that lock, and whenever P1 reaches the halfway point, it just releases that lock. So that
Excellent.
would, yeah.
Yeah.
And similarly for the win flag, it could be like all the threads will try to get the flag like simultaneously. whoever reaches first would obviously be able to get the flag, and like no one ever relinquishes the win flag. So win flag you can only get, but you can never relinquish it.
Sorry. Can you repeat the last couple of sentences?
Yeah. For the win flag, what we could have is just basically a lock, and the only condition for the win flag lock would be that you can only acquire it, you can never release it.
You
So
can never release it.
Yeah.
Then,
so you can never release it.
Okay. Then what other teams will do?
So other teams will keep on waiting. That doesn't matter. We only care about the winning team, right? We only care about the winning team to be recognized.
Okay. So if you try to relate this scenario, the winner who wins the race will celebrate, and other players, other teams will just be staying in the stadium forever.
Yeah.
Forever.
So, maybe a little better technique could be like, let's say the lock is on a log file or something, which basically logs who came first. So basically, whoever the first person to come will get the lock, write his name, and then relinquish the lock. And then we would again have a FIFO view or something, which basically like make sure the ordering is correct.
Okay. Yeah. So whatever solution you proposed is excellent and correct. So last thing is also correct. We can maybe we can understand every aspect in details of Pthreads, but yeah, excellent solution, and it works perfectly well. So I hope everyone is following whatever. What is your name? I missed it.
My name is Sethi.
Okay, so he suggested a correct solution, almost correct, and we'll see how we can implement these things. So whatever we discussed so far are just the concepts, but we also need to implement them in a real way. So we'll go through the solution in the Pthreads. I think I have one comment: barrier concept and lock. Yes, that is correct. So let's see how we implement this. Okay. So 8 players are 8 threads. Barrier for start. Then shared state for halfway mark, means some mechanism to communicate P1 and P2. And then you have exclusive access to win flag. Correct. Now let's go this code very thoroughly and take time to go through each line. So this is the main function for this, and I have set number of threads equal to 8. Right. This is a class of type thread data, which is of size 8. Right. What is thread data? I'm defining this as a team and the player ID. Okay. So there would be 4 teams and there are 2 players, player 0 or player 1. And these are like array of this class type. There is another array of 8 threads. So there is a type called as pthread underscore t. This type is for a particular thread, and there is an array of 8 threads. And then I have initialized a barrier. This is the barrier syntax for pthreads, pthread underscore barrier underscore init for initialize. And I'm passing the address of a variable game start, which is defined as game start of type pthread underscore barrier underscore t. So this variable is of type barrier. Correct. This null stands for there are some argument to this function for init. Otherwise, it will use the default settings for barrier init. And there are number of threads, which are 8. So what this initialization suggests us that there is a barrier and it has a counter. So if you see, this is an integer value, number of threads. It's not a pthread type. Number of threads 8. So it's just an absolute integer value. This means the barrier is initialized to control only 8 threads, right? And now our program starts. So as he said that there can be another thread called a referee, but we can also use that thread as a main thread. So main thread say prints referee says start, and at the start, once this message is printed, we are now creating 8 threads. So how do we create threads? This loop is going from 0 to 8, and in every iteration I am creating 1 thread. So t of 0 will be a new thread data. So this is of type this class, right? Team and team player. And see how I am initializing it. player ID will be 0 or 1 because it is a mod 2 operation based on your out of 8, 4 will be first 0 player and second 4 will be player 1. And then you have a function for assigning team ID. And at this line, you fire a pthread create function call. And now this function called pthread array says that this function call will create a thread of thread 0 with 0 coming from this array of type pthread, right? Again, the null is standing for extra arguments, which is not required. And now there is a parallel task. So this is a function which will get executed when the thread starts its execution. So we'll see how this function parallel task is written. So this actually how we coordinate between different threads, this function. And thread data is like whatever you wanted to maintain the information when the thread starts executing. This function, this object actually the data which you want to pass to the threads. So it's like a thread is a traveler which doesn't know anything what to do, where to do, and this task suggests that what you should do and what all your data you want to operate on, right? This is a function call, and this function call returns whether the thread is created successfully or not. This checks whether thread is created or something, blah blah, and actually it should exit here, exit 0. Any confusion in this syntax on and this design so far of thread creation? Okay. So now go back. Now let's go next to the definition of your parallel task. Okay. So this function we called from the pthread create, right? I hope everyone is following. So once the thread is created, there are 8 threads, and once this line executes, even before the next iteration start for this loop, the thread can start performing this operation. So it may possible that it is already started executing and other threads not even getting created. So only suppose a couple of threads are created and 6 threads are still yet to get created. So what will be the first thing? So the thread need to understand what is the data which I am operating on. So this TD, thread data, was passed as a void pointer. So this is a proper syntax of pthread because any type of data can be passed to this pthread. So always it's a void type of pointer, and you need to typecast it to the data which you know the type of thread data. And this TD has 2 fields, player ID and team ID. So you extract that from this construct, not construct, this object, and then there is a pthread barrier wait. So this means although a thread created initially before another thread, the thread must wait till this point. So similarly, every thread will get created here, and every thread will wait at the barrier. Every thread means P0, P1, doesn't matter which thread it is, it will wait till this line. And so one thing need to understand about barriers, it's only about the count of the threads. So this barrier doesn't wait for a specific thread. So thread 0, thread 1, thread 2, it's wait for a count because we have set the count as a 8. So once 8 threads are reached in this point, so then all threads are good to go. So this becomes our first condition of the start, and all teams are ready because all players are created, all threads are created, they are already in the execution and they are waiting here. So everyone is ready. So now if player ID is 0, so it's like a P1. So this is just a log which I printed to have a log. So printf will say that player P0 of some T started, and then you spend some time to simulate that the player is running, just a dummy loop for spending some random time, and then once the time is finished, it says that it has reached the halfway mark. And now I'm saying there is a shared state of signal player. What it is a global data, which is I have initialized like this signal player array of size 4. Each one holds integer value. And if we recall what I said at very initial slides, that the global data is shared across multiple threads. So this array is shared, even if we have not passed it, but we have the handle to access this data with directly variable name. So signal player of team. So if the team 0 is currently running, it says the player 0 has reached and it is signaling 1. Now if what will the player 1 will do, sorry, player 2 will do when the player 0 is running. So as suggested earlier in the solution, it is just waiting at this location of the array, so team 0, and it is waiting till this value is 0, right? So it's like a busy waiting and not performing anything till this instruction executes. And then once it is comes out of this loop, once it is sets 1, the other threads which was waiting for this will start thread, then spending some random time, finish race, and coming back to the end part of who wins. So I'm using it as a mutex log. So this is a mutex log in a global space, pthread mutex t winner flag. And once it reaches to that point, it tries to acquire the mutex log winner flag. So all other players from different teams are trying to acquire this log once they finish these instructions. And as we know that only one thread is guaranteed to get the log. So after I get the log, I'm checking if the winner flag is 0. So winner flag value is 0 if no other team has reached it. And if it is 0, then I am making it 1 by incrementing it. And then I am saying my team won. Correct. And after that, I am also unlocking the flag. So there was small difference in the solution which was proposed, that other threads will just keep on waiting here and no one will just unlock it. So it should not be happen like that. It should be like you lock it, you check whether no one has reached and hold the flag, unlock. And other threads will also hold the lock, but this condition will be false for them because this flag is already incremented to 1. Clear enough? And this way you come out of this for loop and your program reports the exact simulation of what the game we discussed. So at this point, do we have any questions, doubts? How we implemented it? Anyone?
Just one question for the signal player array, which we are using to like transition from player 0 to player 1, which
Mhm.
passes the message along. So, so this signal player, so basically when I write on like signal player dot like of team is equal to 1, I should like make sure that this information actually reaches the other thread, right? So it should at that point, at that instant, it should actually get flushed all the way to the memory so that the other thread can actually read it, right?
Correct.
So shouldn't it be set as volatile? Because otherwise what will happen is the other thread player will just keep on waiting maybe for a long time, right? It will eventually reach the memory, but the other
Correct.
player could be like kept waiting for a long time.
That is 100% correct. I was about to come to that point. So one thing that if you have observed, I have not used any log here. Although these two players are two different threads accessing the same shared memory, why I did not use log and will it have any implications? The answer is no, because as you said that eventually it will reach, but this thread might need to wait for longer time. Yes, but uh, you can improve it with volatile and it will flush and then every time you read from the memory. But in that case, if you keep on reading from main memory as a volatile, this function call will create a lot of memory traffic unnecessarily. Does that clarifies?
Yeah, that clarifies. So is there a way to don't do full volatile? I'm using full volatile as a very vague term. That by full volatile I mean just flush it all the way to the RAM. Is there a way to just like signal the other thread or like whatever core it is running on, just like interrupt it or something? Is there
Exactly.
a way to do
Yes,
it?
there is. There is. Just wait for few more seconds. I'm going to explain those in the next couple of slides. But you are
Okay,
catching
thanks.
the issues very correctly. Any other issues? Any other issues if you can think of? There is very interesting issue in this. I would be very happy if someone catches that. And let me read the comments. Barrier concept and logs. Does maintain global array is good when we are working in multi-core. I mean re-entrant code. Yeah, so generally we do not encourage global data because global data will not have uh, proper way to wrap it up as a localized access. But I have just simulated this example to make it simple. Otherwise, you can also make it a part of data means the thread data, and pass their pointers to that. And you can allocate those data as a heap allocation and then pass their pointers. So heap allocation is safe in terms of whatever, even multi-core systems we are using, heap allocations, we can convert that code into heap and passing the pointers. Does that answer? I think Mr. Rao. Okay, good. So yeah, so I was asking, thank you. Okay, no issues. That is there any issue you can figure out in this code? Maybe spend some couple of minutes on this, and if someone catches, I will be very happy.
Maybe
And that,
there is another issue, like same problem which you had for single player array, the volatile thing that should also be for winner flag, right? Like the reason I'm saying is that the lock winner flag, the lock which is winner flag, that is a separate variable as from this winner flag variable, right? So what could happen is that, let's say
this one.
Yeah, this one, yeah, exactly.
Okay.
So let's say
You mean value or the mutex flag?
no, not the value
Okay,
itself. So
good.
my suggestion is that this value itself should be volatile. So the reason
Value
I say
itself
this is that,
should be volatile. Okay.
yeah, the reason I say this is, let's say thread one comes,
Mhm.
gets the flag, the value is 0 initially, and it increments it to 1 and then unlocks it, right?
Okay.
Now other like thread 2 comes, it again, like since thread 1 has already unlocked, it can again like lock the winner flag lock, and then when it reads its winner flag value, so what could happen is that the thread 2 could read actually a stale value, right?
So you
If the
so you mean that if thread 0 is writing a value from 0 to 1,
yeah
and maliciously thread 2 can read the flag winner value equal to 0. Does that
yeah
mean?
no yeah, so that's what I'm saying. So the date which thread 1 did may not get flushed in time for thread 2 to actually read the updated value. That's what I'm trying to say.
So you mean that two threads might increment that value to 1?
Yes, that could happen, or could, I'm not sure about like how is it happen, how it is handled in
Okay,
hardware.
so let me answer this question. It's a very important concept. Maybe everyone should pay slight attention to this. So what he's trying to convey, that winner flag value is a variable which is getting shared by all threads, right? And we discussed yesterday by Dr. Kalyan that this will be present in every thread's local L1 cache. And now thread T0 is trying to update it. It updated, and now it is set to 1, and eventually it will get returned to main memory. But same thread, same memory location is also present in, say, T2's L1 cache. And this guy reads from its local memory and says that this value is 0 because that update which thread 0 started is not reached to the L1 of that. And it may also increment it to 1 and also say that I am the winner. So issue is very clear, and there is a subtle thing in this. So internally, when locks and unlocks are implemented, so that's why when I say that locks implementation is a complex thing, internally lock implementation do use flush instructions. So there will be a guarantee that before a lock acquisition, whatever there is in your memory, in your local cache should be flushed in the main memory. And when you unlock it, the update which happened in between, they should also be flushed internally automatically by unlock function call. So the scenario which you are referring to uh, is possible, but not in terms of if you are using mutex log from Pthreads. So it internally handles that memory fences.
So there would be an implicit memory flush effectively when I'm acquiring a lock.
So yes, it will be an explicit, I would say, by the implementation of logs, but
Okay.
implicit for a programmer.
Okay, got it. Thanks.
So that's why. So lock implementation is a complex task. So it involves a lot of stuff. And my first bullet, if you remember, that was you need a proper understanding of hardware and what hardware offers to you. So yeah. So yeah, I think this answers your question. And this lock unlock ensure that this doesn't happen like that. So that is not an issue. There is another interesting issue which I was trying to convey. But anyway, I think we have enough time, but let's discuss what I wanted to convey. So as correctly pointed out by the place where we are signaling this. So what will happen that this P0 is spending time in his first half of race, and P2, although it is created, it is performing this while instruction. And this while instruction is going in a loop. This is called as busy waiting or a spin log. So you are spinning on a certain value, and there are different literatures how you spin it. Locally, you spin from flush from or take it from RAM or whatnot. But even if you for a moment you forget about it is rotating on a cache or a main memory, it is also unnecessarily consuming CPU cycles. So it is not doing any useful work in this busy waiting. So it is just eating up the resources which are there in the hardware, right? So there is another construct called as conditional weights, which is like I would say the summarized tagline, let me know I am waiting, right? So thread 0 is doing some task and thread 1 is waiting that thread 0 should signal me when it is done. Let me go to the comment. Pooling. Yeah, thread pooling is also there. So yeah, so like a thread preempts from the current execution. Yeah, that is true. So yeah, so I'm trying to introduce the concept of conditional weights here. So thread 0 should signal thread 1 that I am done. Now you should start. And so that thread 1 is not unnecessarily spinning or wasting CPU cycles. So this construct is called as conditional weights. So again, going back to our Pthread setup. So this looks something like this. So you declare a variable of type conditional variable, conditional weight, Pthread condition underscore t, and you initialize it. You also declare a mutex variable log and initialize it. And now, suppose thread 1 wants to do some important task, and thread 2, but it is waiting for thread 1 signal, right? So thread 1 acquired a log, and then thread 1 is saying, I am waiting for this condition variable, which is there is a typo. It should not be condition 1. It should be condition 1 here. In this, it should be condition 1, cond 1. Okay. And there is another mutex variable. And at this point, it is getting blocked because this condition is not yet satisfied or the mechanism doesn't signal that. And meanwhile, this thread T2 is acquiring this mutex log. And then if it is fine, this thread wants to signal this, he can go, he said, Pthread conditional wait signal. So these signals here, you can start now. And once the signal sets some value to this condition, this wait unlocks itself and then do whatever task you wanted to do and finally unlock the mutex. Any question on this? I guess it is slightly confusing things are here, but I would like questions to come from the audience. So it's simply like one thread is signaling, one thread is waiting for the signal, just like that. This is the friend you are waiting for signal, and this is the one who is waiting for something. And the mechanism, it something works like this. You have a mutex log, you acquire it, you check the condition, and this mutex, although it looks like there may be a deadlock because you are taking a mutex log here and unlocking here, and then you may ask that how this thread T2 can acquire this log because this thread is waiting. Anyone has this question in mind? Because it's a very obvious question that the one scenario which I expressed, that it may lead to deadlock. So this may also lead to deadlock, right? So you cannot acquire this log. But internally, how it works, when you call the conditional wait, this goes into a block state. Block means the thread is getting blocked. It is ideally getting preempted from CPU. Preempted means it is not running on CPU and it is unlocking the mutex internally. Correct? It is unlocking the mutex internally. And when this thread tries to signal, it will acquire this unlocked mutex here. Then it signals this and unlocks. And then when this guy awakes itself, it internally acquires it, do something useful work and unlocks it. So why we are doing all this hangama if we can just do spin lock, right? The hangama is because we don't want to waste CPU cycles. And thread 1, if it is not doing any useful work, it should get kicked out. And this mechanism ensures that you are not eating up the CPU resources. Yeah, as simple as this, not many complications. Now I would like to introduce a very interesting concept in the parallel setup. That's what I was trying to get from you guys, that can you come up with some other issue with this? So correctness wise, there is no other issue, but a scenario which is very interesting. It's called as false sharing. So this connects all dots to your yesterday discussion, which Dr. Kalyan discussed, that the data is shared with the multiple cores in a blocked fashion. So you have discussed yesterday MISI protocol, MSI protocol, and all the discussion rotated around the cache block. The block is dirty, the block is shared, the block is something, the block is something, right? But we never discuss anything on the granularity of a memory location, right? So consider you have an array. By the way, the cache block size is 64 byte in all general CPUs these days. 64 byte means you can fit only 8 variables of size 8 bytes. So in this case, if you have int of 8, this should be like int 64, but suppose this int has a 8 bytes or even 6 bytes, it's also fine. It's still a same block. So what happens? So when you allocate this array, that array allocation happens at some locations in the memory. And suppose this allocations starts from block 0 and goes like this. And there are such different blocks in the cache, and this array fits into a single cache line because there are only 8 elements, each of size 4 bytes. It is only occupying 32 bytes of it. 8 into 4, 32. Clear enough? And now suppose thread 0 is accessing on the 0th location of this. So it wants to update my array of 0 location to 10. There is another thread 2. This is a thread 1 typo. So another thread T1 is accessing array location 1. So there are 2 different threads operating on 2 different memory locations, right? Now, do you think there is any concurrency problem here? Do I need to acquire locks for this? Yes or no? Any suggestions? Because these 2 threads are operating on 2 different memory locations. Yes or no? No need for locks, correct. But there is a subtle problem with this. Now go back to your yesterday discussion. Once this update happens, the block B0, which was there in the L1 cache of thread 0, is set to dirty, correct? And once the block is dirty, there are all stuff which happens from invalidations sent from that L1 of thread 0 to other threads and also for main memory. And then you get the fresh copy. And then when thread 1 wants to write on this location, it also invalidates the copy and writes to it. Although every thread is writing on different locations, eventually the data which is written on main memory RAM is consistent and is desired whatever it used to be. But it is creating unnecessarily a lot of traffic to the NOC, the network channels, and that is going to degrade your performance. And eventually at the memory level, all writes of such things are happening in a sequential order. So this write is happening first at memory level. Then eventually when blocks are settled as a dirty ownership and all exclusiveness is shared, the other thread also writing to this. So all these writes, although they are appearing, they are writing different locations and different threads are writing, they look to be happening in parallel, but at memory level, they are happening in a sequential way. This scenario is called as false sharing. So you are not sharing, but you are sharing as a cache block. Understood the concept? Any doubts in this? Yes or no? You can unmute if you want to. Okay, I hope everyone could follow what I was trying to convey. Okay, no, it's clear. No def log, it's clear. No. So any solution for avoiding such things?
Maybe
Can
just
I?
place the two like variables 64 bytes apart, right? That would guarantee basically the separate cache.
Correct. This thing called as padding. So if I redesign this implementation like this, so you have an array of 8 cross 8 and you are placing it such a way that once you have uh, like the first column of this 2D matrix, this one complete line covers the complete cache line, say B0, second covers B1. Although this memory is getting wasted, but now when every thread is writing their own things, same type of is should be thread 1, and now every write is on separate cache line. So these writes can go in parallel and they do not create any false sharing. So does that mean that whenever such scenario appears, I should change my design from this to this? The answer is no. Only if your threads, your writes are too frequent. So your threads are frequently writing on such side by side locations, then only it will really create any bigger difference in your performance. If it is writing once in a while, that it does very large job in between and then just for syncing it is just writing, then you won't be able to see any bigger difference. But if you want to just try out this example, just write a small code and just try writing these things, like Pthread or OpenMP, you will be able to see these differences, right? So these are the few interesting things which do appear in this parallel setup, and that's how you should avoid or you should rethink your design. And the issues might not be apparent very easily, but the reason might be hiding very deep inside the concepts of hardware and concurrent programming. Okay, so now we are at ping-pong mechanism. What does that mean? Can you unmute yourself, Mr. Rao?
Hi sir, Koti
Hi.
here. My intention is instead of going for the two-dimensional with the padding, it is memory wastage, right? With the existing memory, can we do ping-pong mechanism like
What
creating
do
the
you mean by ping-pong?
blocks? Suppose I have a 256 kilobit means I can divide it as a 128 kilobit and 128 kilobit. One array 0 should go into the first ping buffer, and then array 1 will go to the pong buffer while writing. Is that work in the threads concept?
So actually, I did not able to follow what the solution. So do you mean that you can like
Yeah.
solution to this or what?
Yeah. Solution this only 0,
Okay.
1, 2, 3. I can make it as a one bank. 4, 5, 6, 7. I can make it as a another bank. So my array of 0 will write into the first bank,
So you mean
and
the
then
bank of RAM,
yeah,
bank of
memory,
RAM or cache block itself?
memory. I'm telling RAM. Yeah, SRAM.
Okay, yeah.
So if I divide this entire memory into two banks, then we can avoid this false sharing. And it's just thought only. I'm not sure in the threads concept like how it will work.
I'm not sure, because if I understand whatever your solution you're proposing, the bank, you mean that you divide the RAM itself into two parts?
Yes. Yeah. Instead of going for the two-dimensional memory, it will consume 8
No,
cross 8.
so when I said this solution is not about the full RAM, I'm just saying when you have this small size, like you have 8 threads,
Yeah.
so you create just like a padding for each location, so that you are not using other locations, but you're separating out each location as a separate cache line.
Okay.
So this is not a complete RAM. This is just a small piece of memory. It's 8 cross 8, 64 into 64 bytes.
Yeah. Okay.
And this is a logical layout. So the RAM itself is a sequential. All those addresses are sequential
Okay. Yeah.
in address space.
Okay. Thank you.
Yeah. Thanks. So yeah, so we are about to finish whatever I wanted to discuss in this talk. So as a summary, concurrent programming is an art. You need to think in the different aspects like memory, RAM, sharing of data, and still try to extract a better performance. And concurrent access to shared memory can lead to data races. So you need to take care of such things. Synchronization constructs offer tools to design the correct parallel programs. So there are tools. The responsibility of designing proper protocol is on the programmer. So you should properly use logs, barriers, conditional weight, automix whenever they are required. And also you should avoid deadlocks, busy waits, fault sharing, all such scenarios. And always keep in mind that parallel program is very hard to debug. So correct answer may never lead to or may never able to prove the correctness of program. Proper using of such constructs can only prove the correctness of your program in a theoretical aspects. So yeah, at this point, I would like to thank everyone for listening to this couple of hours, and I would like to take questions if any. Thank you.
I had one question related to false sharing. So
Mhm.
we were talking about how we can prevent it. So the way I understand the problem is that there would be a lot of cache communication going on, like lots of invalidations, and so
Yes.
basically like thread 1 invalidates the copy in thread 2, then brings it to its own cache, then thread 2 invalidates thread 1's copy. So like the data would be moving like all over the place. Like that's the
Yes.
main problem, right?
Yes.
So one like potential solution, which I mean there are some drawbacks to it, but what I was saying is that maybe let's not even let's like for example, if the compiler could somehow identify like these are the variables which have potential to be false shared,
Mhm.
what it can do is they can like just set up a like parameter or something to that variable, which basically tells the CPU to just do not bring it into L1. It just basically puts it into L2 or something. Like basically L2 would be common between. I'm assuming that processor P1 and P2 have a common L2, right? That's the assumption. What
Uh,
would happen is that
mhm.
what would
Okay.
happen is that the data is not brought into L1. It just stays on L2 itself. Now the thing is that what I've avoided is I've avoided a lot of data movement because the data, since it never came to L1, there
Mhm.
is no need to remove it from L1. I can just simply invalidate in L2 itself. The invalidated signals would still be there, but the data movement would not be there.
So you mean the L2 is the shared one, right?
Yeah, L2 is shared. L2 is shared, and then we have like sub memories of L1, like thread 1
No,
L1 and thread 2
generally,
L2.
actually, L2 is also shared. So L3
Yeah.
is sorry, L2 is a private cache.
Okay.
L3 is shared.
Yeah. So L3,
L1,
like,
L2 are private
yeah.
caches. Yeah. So there can be mechanism, but in all modern CPUs, how they are designed, they are generally use inclusive caches, so that processor
Okay.
always uses data from L1 cache.
Yeah.
So typically, so even if you find something cache miss at L1, so
Yeah.
data brought from the RAM to L3 to L2 to L1, there can be some bypasses and data can be directly available in the buffer.
Yeah.
But yeah, this solution can be possible. We need to just add proper instructions in a compiler optimizations.
Yeah.
And yeah, so whatever we can do as a manual programmer, all smart tricks can be added to compiler. But that is a different topic. So what all things can be done in compiler, how difficult they are, how difficult to infer something from static analysis and add as optimizations. Because at compile time, you do not have any runtime data.
Yeah.
You do not have information of what thread is doing, what is the value of that variable. So things become very difficult to correctly infer at compile time.
Okay.
So if it is easy to implement at a, I would say at programmer end, so things are very easier. Yeah, so I
Yeah.
think that's how it works. So compilers is do possible, but it's difficult stuff. And
So does the
if you can,
ISA? Yeah.
Mhm.
Sorry, you were saying something.
No, I think yeah, you can continue.
So I was asking that does the IS like AMD 64 have support to like label a cache block as saying that okay, this is prone to false sharing and I'm going to set its affinity to L3. So basically the block never comes down to L2 or L1, it just stays at L. So is there a way to like fix that block, like set up affinity to it, saying that it will always stay as L?
I don't know precisely whether you can tag some bit to a cache block, but there is one provision always that you can place a block or you can request a priori a block to
Yeah.
sit in certain cache level. So if you want to bring some
Okay.
data from RAM to L2,
Yeah.
and the data will be there in L2 for sure.
Yeah.
that you can do, but I'm not sure that you can restrict the data not to be appear in L1.
Okay.
So
Good.
I guess that is not there. So general CPUs do support this conventional design of L1, L2, L3.
Thanks.
Yeah. Any other questions on any topic?
Thanks, Kalkar.
Yeah, I think we are
Uh,
almost at 7.
Yes. Thank you very much. Thanks for giving very enlightening talk.
Thanks for the opportunity, by the way, Dr. Praveen.
Yeah. Thank you all. Tomorrow we have a lecture on synchronization techniques. In that lecture, we are going to discuss about different types of synchronization techniques. See you then.
Okay. Thanks everyone.
Thank you, sir. Thank you for the
Bye.
great lecture. Thanks a lot.